title doesn't make any sense. Yeah, and the guy wears a suit. Do you think he wants to sell something? Yeah, maybe. Think we should leave? Well, lunch isn't ready yet, and there is not any other talk to watch, so let's stay there. Yeah, I think you should stay. Maybe this talk will blow your mind somehow. So, let's start with a very simple question. What is FP good for? Well, it's very good for modeling data. We have immutability by default, helping us sharing data across threads and so on. We have algebraic data types, we have pattern matching, we have type classes. Modeling data is really, really cool with functional programming. Functional programming is also cool to model effects. We have plenty of solutions to make our side effects more tractable. We have Zio, we have Katz effect, we have plenty of stuff. So we have pretty much good tools using functional programming. And in the end, our functional programming applications look like tiny little boxes. Inside the box, everything is pure. We only have functions. And we push everything that is dirty on the side. That's maybe what we call that side effects, right? But the problem is, we still need to make our boxes communicate with the external world, meaning that data needs to get in and out of the box. And that's a problem. Because in every project, we still need to write some code to serialize data, for example, in JSON, or maybe Avro, or protocol buffers, or thrift, or probably 3 other flavors of JSON. We also need to write code to validate our user inputs, or to read configurations, to talk to database, to, I don't know, generating random data for our property-based tests, or pretty-printing, or comparing value. It's a lot of code that only depends on the structure of the data, not its semantics, right? And still, we need to write code to handle that in every project. And in every project, this code is repetitive, it's mechanical, it brings no business value. So we need to find a way to abstract that away, right? So what can we do? In Scalar, we have one idea for that, is that let's scrap that boilerplate at compile time. And we have plenty of solutions to do that. We can use our plain old macros, or shapeless, or Magnolia, Scalar Deriving. And for specific tools and needs, we have a bunch of specialized libraries like Saucy or Scodec or whatnot. But we end up with many different APIs that are not always easy to customize when, we have some edge cases to handle. Most of them slow down compilation. Magnolia and Scalar Deriving are a little bit better on that than shapeless, but still, it slows down compilation, and Scalar C doesn't need to be slowed, right? And most of the time, the error messages aren't really helpful. But it gets worse. There is one problem compile time derivation cannot solve. And this problem is all over the place, and it breaks your project in very subtle cases. The problem is that your code needs to evolve. And the data you put on the wire, it will be there forever. So at some point, you will lose the synchronization between your code and the serialized data, right? Let's take a quick look at what we call the evolution problem. Say we have a system, a distributed system with 2 nodes. And our nodes share messages with each other. A message that in the payload has a field called name and a bunch of other fields. And let's say in a future version of our code, the name field becomes first name. What happens if we deploy this new version on only one node, because we cannot deploy on every node at the same time? So we deploy the new version on node 0, and now, in the code in node 0, the field name doesn't exist anymore. We have a field first name. And since we derived serializers and deserializers from the code, the new deserializer cannot read the messages that hold a field called name anymore. So it breaks. It's a problem of backward compatibility. And of course, on the node 1, which isn't deployed to version 2 yet, the new first name field isn't known because the deserializer was derived at compile time. So in every project that is significant, we end up with these kind of problems. If you do event sourcing, you have a very hard time when you need to change your event schema, and so on and so forth. And compile time derivation cannot help us on that problem. It's very, very sad. Most of the time, you end up, I don't know, carrying all the old versions of your ADT in your code base just to be able to derive your serializers and deserializers from that. And your code base becomes a big ball of mud. So what if we manage to solve this very big problem and then get something free on top of that? So before we dive in solving the evolution problem, let's see what we need. We need a way to, as Shapeless or other libraries do, to abstract over the structure of data. From this, and this abstraction need to be available at runtime, because that was the problem with compile time derivation. It's that it happened at compile time. And from this abstraction, we will derive a whole bunch of operations. So let's see how it goes. This abstraction we need, it exists, and it's called a schema, right? Let's see what we mean by schema. The A in ADT stands for algebraic. We can think about our algebraic data type as the result of using an algebra. And this algebra is really, really simple. It's composed of only 3 things. We have unit, we have the sum, the binary sum, which we can approximate with either, and the binary product, which is just a tuple 2, right? And with that, we are able to represent any possible data type. So let's take very simple examples. The bit data type, which is only 0 or 1, can be represented as either unit. The byte, which is 8 bits, can be represented as this very strange product of 8 bits. We only have binary products, so we'll need to, nest these things. But if you squint out enough, it's the same thing, right? You can convince yourself by just counting the inhabitants of these types and make sure that it matches with what you're trying to represent. For example, and you need to know that unit has only 1 inhabitant, of course, it's unit. A sum has as much inhabitant as its 2 branches, and a product has as much inhabitant as the multiplications of the inhabitants in its 2 branches. So let's try and count. Either unit has 1 plus 1 inhabitants, that makes 2. That's as much as the bit type, so we're good to go. And if you do a product of 8 bits, you do 2 times 2 times 2 times 2 8 times, which means 2 to the power of 8, and that's the same number of bytes we can come up with. And this goes on forever. For example, option is just either an A or unit, and unit will be used to represent none, and so on. And you can even represent recursive types in that manner. It's slightly difficult to express it in Scalar, and hopefully you don't see that error there. But you could say that a list is either unit, for the nil case, or the pair of a head, an A, and a list, recursively. The problem is, in the type system, the Scalar type system, you cannot represent recursive abstract types. But that's not a problem. So let's move on. Of course, this principle works with our concrete case classes and seal traits. A case class is just a product, and a seal trait is just a sum. So in the end, we should only need these three things to be able to represent any possible data. So we have our abstraction we are looking for. We have unit, the sum, and the product. That's it. So let's see what we can build on top of that. Of course, using only that wouldn't be very, very convenient, because you don't want to be typing bit or bit or bit or bit or bit and so on forever. So we'd need a bunch of helpers to make that convenient. So, for example, we need a way to represent correctly records and unions, which are sum and products and sum with labels in each branch or each field. We also probably would need some primitive types to avoid writing either unit or unit, and write directly bit or Boolean, for example, and so on and so forth. I won't dive into the details for that, but I must tell you how this is possible. And this is possible thanks to the notion of isomorphism. An isomorphism is merely a pair of functions that are inverse of one another, right? And so when you have a schema for a type A and an isomorphism from A to B, it's all you need to be able to talk of the type B as a schema. So schema of A plus iso AB gives you a schema of B. And in an imaginary library where we can define schemas, let's say this is the schema for either unit. Then you just plug onto it an isomorphism from either unit to Boolean, and boom, you have a schema for Boolean. So using unit, sum, product, and isomorphism, we have all we need to represent any data type in a convenient way, almost. OK, so now what? We weren't talking about schemas. We were talking about the evolution problem. But before going into the evolution problem, I need to convince you how schemas can be useful. So the last thing we need to do with schema is to come up with a way to use them. And the idea is to use them to derive some operations. What do we call operations? Simply, an operation on A is anything that resembles a function that talks about A. So a function that takes an A, or a function that returns an A, or a function that do both, right? And most of the time, instead of saying operation on A, we just say f of A. So an example would be your JSON serializer. It's like a function that takes an A and returns some JSON document. Or a JSON deserializer. It's something that takes a JSON document and returns an A, and so on. This is the kind of operations we will be able to derive from our schemas. And the idea is quite simple. It's just a matter of going from, regardless of the A, from a schema of A to f of A for any possible A. This has a name. It's called a natural transformation. And in most libraries, it's denoted with this squiggly arrow. So deriving an operation from a schema is just coming up with a natural transformation from schema to this f, right? And I promise I won't go into the details on how this is done. I gave a talk about that last year, roughly. But the idea is that a schema is just a tree. So if you're able to transform each leaf of the tree into an f of some x, and then to combine these smaller f's into bigger ones, depending on which node you're in, you will end up with a big f of a. So for example, if we are at a product node, and we have on the left an f of x, and on the right an f of y, we should be able to combine these two to produce an f of the pair xy, and so on. And if we are able to do that, we will end up with our natural transformation from schema to any f. OK, so that was a big parenthesis, talking about schema and introducing the concept. But what we want to solve today is this evolution problem. So let's recap the evolution problem. We've understood the problem, but what we don't want is to carry along all the old versions of our ADT to just be able to read old data or data from the future. We need to implement two things, which are backward compatibility and forward compatibility. Backward compatibility is being able to read old messages, and forward compatibility is being able to read new messages from the future. So the important word is to read. We'll solve the evolution problem just by coming up with readers, alternative readers, able to read messages from other versions of the code we are running. So let's try to devise a strategy. First, we need to define a set or list of possible migration steps between two schemas that allows for backward and forward compatibility. This set is finite. It's just a matter of expressing it. For example, you could say, I want to add a field with a default value. That is the kind of migration you can do while guaranteeing forward and backward compatibility. Then we will use this migration step to express the other schemas, the schemas of the other versions of our ADT, in terms of the current one and some step that goes from the other version to the current one. Then we will use these new alternative schemas to derive alternative readers, and we should be good. So let's dive a little bit into the details of that. So our migration steps is just a regular ADT with classes representing the steps. So for example, we have add a field that needs, it's important, it needs a default value, because otherwise you cannot implement the backward compatibility, forward compatibility actually, or backward. And so on and so forth. You could say, I can rename a field. I can do plenty of things that doesn't break that compatibility. So you just materialize that into a regular ADT. Then you could, in this imaginary library expressing schemas, express, and that's important, the other schemas in terms of the current one. So for example, let's say I have a person data type in version 2. It's my current one. I just don't write it here. I could derive this one at compile time. That's OK, because it's the current one. No problem at all. Then I just want to express how I came up to this current version from the old ones. So what I say is, using the person dv1, if you go from the V1 and you add a field called age of type int with default value 0, then you end up into the current version. All right? It's the other way around. But that way, I only ever mention the current type, the current person type. I don't need anything from the past to define this old schema. And so on and so forth. I could say for the V0, the very first version, going from V0 and renaming a field from name to username, I end up with in the V1, and so on. So this is a way to express the past in terms of the present. Okay? So we could skip that step and do things manually and come up with this alternative schema by hand. Let's say that in the same migration history, we have our current person class, which has an age field of type int, username, and email. And how do we express the schema of the old version in terms of the types we currently have just there? It's quite easy. It's just a matter of plugging an isomorphism on top of the current version. So it just says that we still use the current schema, but we say that we go from this old representation of the previous version of the person type that didn't have the age field, so it was just represented as a pair of strings, to the current type, the current person type. And what we do is, when we get a pair of strings, we plug the default value for the age field, and we use the other data to come up with the person. And in the other way around, because it's an isomorphism, which we need to go both ways, in the other way around, we just forget the age field, because it wasn't defined in the previous version. So using that, and deriving serializers from that, we are able to talk to older or newer version of the applications. And finally, when we have our alternative schema, we just reuse the mechanism I just mentioned before to derive our readers and writers. So that way, I think we solved the evolution problem. Something that no existing solution can do, because they rely on compile-time derivation. We never have to keep our old entities into our code base. Writing the migration is quite easy. It just takes a few lines. And everything else works as easily as it did with automatic generate derivation at compile time. But that's not the whole story. Having schemas, the correct abstraction about the structure of data, and this mechanism of derivation, we have a lot of things that comes for free. You could, for example, have Scalar check generators with just a line of code. You could, I don't know, have equality type classes with just a line of code. Or orderings. You can also have show, a nice show instance to pretty print your data in debug with just a line of code. You can have forms and UIs. You can derive the UI and the forms from the schema. And so if you need to change your schema, the form is automatically updated. You can have, I don't know, serializing and deserializing in Avro in just a line of code. You could also use that for your SQL migrations. From the migration I showed you earlier, you could derive SQL scripts that will apply the same migration on your database. And finally, you can go completely crazy if you add on top of that an abstract representation of data, not just its structure. you can build completely generic data pipelines that just perform a lot of complex operations on data that you never wrote a case class for. It's just a schema. You plug a schema, and you have a new data pipeline. So this technology almost exists. It's not an imaginary library. It's called Scalar Schema. It's under very active development by a large team of 2 people, including myself. We already have the correct structure for the data structures. We have the derivation mechanism, and a few derivations are implemented. We are still working on the migration stuff I showed you, because the code is a little bit more complicated than that. I mean, the internal code. So your help will be very, very welcome. And I think that's it. I'd like to thank, special thanks to John Deckers, who initiated the Scalar schema and helped me to review this talk. And to Dominic, who is the other half of the Scalar schema team and was a delight to work with. And I think he's searching for a job now, and he is in the room, so he's here. So go and find him before someone else hire him. And that's it. That's me. I'm Valentin. I'm working at 47 Degrees, which is a marvelous company, and we are hiring. The website is on the slide. And because I am a man of my words, a few weeks before, I vote that if this talk and the library doesn't change your life, I will give you a hug. So I'll be around and giving, hopefully, not that much hugs for the next 2 days. Thank you.
Thank you. Are there any questions?
Or hug requests?
Okay, so I have, sorry.
I think
there is one?
What about the overheads?
Okay, still.
What about the overheads? You mean at runtime? Well, the derivation happens at runtime, but it happens only once. It's like, you can think about it as type class derivation. You derive the first time you use or at the bootstrap of your application. So afterwards, you don't pay any penalty.
Do you have benchmarks for how the derived code actually works?
I didn't.
Benchmarks.
We don't have benchmarks yet for the derived type classes, but we have an issue to add them. So if you want to jump in and add benchmarks, I would love that. Yeah. Honestly, right now, the derived functors probably aren't as efficient as the one you would write by hand, because we go through this internal representation in terms of nested tuples and stuff like that. But there might be a way to avoid that. So if you want to work on that as well, you're welcome. Any other questions? Okay, thank you.